Valence bond theory is another basic theory developed to use quantum mechanics to explain chemical bonding. According to this theory, a covalent bond is formed between two atoms by the overlap of the half-filled atomic orbitals in the open shells of the atoms. The two electrons occupying the overlapping orbital are shared by the atoms. Because of the overlap, it is most probable that electrons should be in the bond region which bound the atom together. For example, in a hydrogen molecule, two electrons are shared by the hydrogen atoms in a covalent bond formed by the overlap of their 1s orbitals. The valence electrons belonging to an atom and a molecule include both the shared and unshared electrons. The electrons shared by two atoms are counted twice, once for each atom. For example, in a hydrogen molecule, each hydrogen atom has two valence electrons, both of which are shared electrons. The valence electrons can be represented using dots. Gilbert and Lewis extended the concept of the electron dot diagram by using line between atoms to represent a shared pair. The octet rule is a chemical rule of thumb that light main group elements tend to bond in such a way that each atom has 8 valence electrons. The quantum theory of the atom explains the 8 electrons as a stable closed shell with an s2p6 electron configuration like a noble gas. For example, the neon atom ground state has a closed L shell. According to the octet rule, the atoms immediately before and after neon in the periodic table, i.e., carbon, nitrogen, oxygen, fluorine, sodium, magnesium, and aluminium, tend to attain a similar configuration by gaining, losing, or sharing electrons. The octet rule is especially applicable to carbon, nitrogen, oxygen, and halogens. For example, in a fluorine molecule, each atom shares 2 electrons with the other atom, one from the atom itself and one from the other. Thus, each atom has 6 unshared electrons and 2 shared electrons, so that both atoms are considered to obey the octet rule. In an oxygen molecule, each atom shares 4 electrons with the other atom, 2 from the atom itself and 2 from the other atom. Thus, each atom has 4 unshared electrons and 4 shared electrons. In a nitrogen molecule, each atom shares 6 electrons with the other atom, 3 from the atom itself and 3 from the other atom. Thus, each atom has 2 unshared electrons and 6 shared electrons. The bond order is the number of shared electron pairs. So, fluorine, oxygen, and nitrogen's bond orders are 1, 2, and 3, respectively. The resulted bond orders are the same as calculated using molecular orbital theory. Not all electrons in the valence shells are shared by atoms. A lone pair refers to a pair of valence electrons that are not shared with another atom. For example, each fluorine atom has 3 lone pairs in a fluorine molecule. Each oxygen atom has 2 lone pairs in an oxygen molecule. Each nitrogen atom has 1 lone pair in a nitrogen molecule. In a methane molecule, the carbon atom shares 8 electrons with 4 hydrogen atoms, 4 from the carbon atom itself and 1 from each of 4 hydrogen atoms. The bond order is 1. The hydrogen atoms do not obey the octet rule because they can form a closed shell like helium with 2 electrons. The octet rule is also applicable to ionic bonds. For example, the first ionization energy of sodium is 5.14 eV. Sodium will very easily lose an electron to form sodium cation with a closed shell as in neon. The first electron affinity of chlorine is 3.62 eV. Chlorine will very easily gain an electron to form chlorine anion with a closed shell as in argon. The energy required to transfer an electron from a sodium atom to a chlorine atom is easily offset by the electrostatic energy between the ions. Valence bond theory adheres to the idea that electron pairs are localized between 2 specific atoms in a molecule. An example is the valence bond description of benzene, suggesting that the structure contained a ring of 6 carbon atoms with alternating single and double bonds. 24 of the 30 total valence electrons are shared by carbon and hydrogen atoms to form 12 sigma bonds. The remaining 6 electrons are shared by carbon atoms to form 3 identical pi bonds. In molecular orbital theory, electrons are distributed over the entire molecule. For example, the 6 pi electrons are delocalized in 3 molecular orbitals spanning all 6 carbon atoms with 2 energy levels. Experimental results show that all carbon-carbon bonds in benzene are chemically equivalent, and the pi electrons have 2 ionization energies. Therefore, delocalized molecular orbital description is more appropriate for large molecules. Classic valence bond theory cannot explain the magnetic properties of some molecules. For example, oxygen obeys the octet rule with a double bond containing two pairs of shared electrons. However, the ground state of this molecule is paramagnetic, indicating the presence of unpaired electrons. Molecular orbital theory can predict magnetic properties in a straightforward manner. Modern valence bond theory's explanation to the paramagnetism of oxygen is more complicated. Pauling proposed that this molecule contains two 3-electron bonds and one normal 2-electron bond. The octet on each atom then consists of 2 electrons from each 3-electron bond, plus 2 electrons from the 2-electron bond, plus 2 electrons from a lone pair. Each 2-electron bond counts as one bond while the 3-electron bond has only one shared electron and therefore corresponds to a half bond. The bond order is 1 plus 0.5 plus 0.5 is equal to 2. The bond order is the same as calculated by classic valence bond theory and molecular orbital theory. Classic valence bond theory cannot explain the stability of some molecules either. For example, carbon monoxide is sometimes represented with a double bond. However, the carbon atom in this structure does not obey the octet rule. Following the octet rule for both carbon and oxygen, the two atoms form a triple bond, with 6 shared electrons in 3 bonds, so that carbon monoxide is isoelectronic with molecular nitrogen. One of the bonds is formed by 2 electrons from oxygen. This bond is a coordinate covalent bond, in which the 2 electrons derive from the same atom. The coordinate covalent bond causes a polarization of the molecule, with a small negative charge on carbon and a small positive charge on oxygen. In contrast, molecular orbital theory can predict the stability and bond order of carbon monoxide in a straightforward manner. Some stable molecules and radicals, such as nitrogen monoxide, have odd numbers of electrons. They obtain octet configurations by means of 3-electron bonds. In nitrogen monoxide, the octet on each atom consists of 2 electrons from the 3-electron bond, plus 4 electrons from 2 2-electron bonds and 2 electrons from a lone pair. The bond order is 2.5. Molecular orbital theory can predict the stabilities and bond orders of such kind of molecules in a straightforward manner.